My name is Mike Mulligan. I'm a professor of cell biology here at University of California at Irvine. Today I'm going to give a demonstration about chlorophyll fluorescence. Chlorophyll is a very wonderful molecule. It is fundamental to the process of photosynthesis, and it does something very special, and that is it's able to absorb light energy and hold on to that light energy in an electronic fashion. And today I'm going to give a demonstration that illustrates that. So to start with, I'm going to use some spinach leaves and in a mortar and pestle, and I'm going to grind the spinach leaves with some acetone. So I'll put a few leaves into my mortar and pestle. I'm going to add some acetone, and then I'm simply going to crush the leaves. And this allows the chlorophyll to be extracted out of the thylakoid membranes. The chlorophyll is in a very special environment inside in the thylakoid membranes, which allows it to perform its function. We're going to extract the chlorophyll into an organic solvent, acetone, and we will see some of the primary principles of how that works. You can cut. After extracting the chlorophyll from the spinach leaves in acetone, I transferred it to a small centrifuge tube, gave it a quick spin to clarify it, and this you can see is the green solution, chlorophyll and all the other pigments from the spinach leaves being solubilized into acetone. Okay? And basically, what I'd like to do is now give a demonstration of the fluorescence of chlorophyll. In order to do that, when we look at chlorophyll, we see a green solution. The reason chlorophyll is green is because it absorbs red light and blue light. Okay? It lets the green pass. If chlorophyll absorbs red light or blue light, these electrons go to this excited state, and that allows chlorophyll to perform some of its functions in terms of energy conservation. When chlorophyll is dissolved into a solvent like acetone, it's no longer able to perform the special functions that it does in the thylakoid, but instead the energy is dissipated as fluorescence. Now, chlorophyll fluoresces red light. Okay, it absorbs blue light and absorbs red light, and it fluoresces a slightly longer wavelength of red light that has slightly less energy. However, when this chlorophyll right here is illuminated with white light, but we can't see any fluorescence because there's so much white light in the room. Now, in order to observe the effect, what I'm going to do is I'm going to illuminate the chlorophyll with UV light, which is shorter wavelength, higher energy, and it's a wavelength of light that our eyes can't see. This wavelength is dangerous. It's the stuff that causes your retina to burn or your skin to tan or get cancer. So I'm going to be protected with a UV shield here and a UV shield here. Okay. Now, what I'm going to do is I'm going to take a dilute solution of chlorophyll like this, and I'm going to transfer it into this large beaker. Okay. And in order to see the effect, I'm going to need to turn the lights off. So bear with me for just 1 minute. Okay. Now, with the lights off, I'm going to illuminate the chlorophyll with the UV light box. This is a UV light source underneath and the shield above. And now you can see when illuminated with UV light, it shows a nice red fluorescence. This is because the chlorophyll is absorbing light energy from the UV light going to a very high excited state, decaying to a state, and then it drops back to ground state and emits a photon of red light. And this illustrates how chlorophyll is capable of holding energy and then using it for productive manners. Okay, now this is the chlorophyll solution. I'm going to add a little bit more chlorophyll. You can see it actually, the concentrated stuff goes red. I'm going to add some, and you can see as I add it how intense the red fluorescence is. Pretty cool, huh?